Okay, so we are studying vectors, right? In linear algebra, it's pretty much all about vectors. So let's start by trying to project one vector on top of another. So this is a vector. Okay, so this is a vector, and let me try a different color. Okay, so this is another vector. That's not a different color, right? So this is a vector, and this is another vector. Now let's say what we're trying to do. We are trying to project, let's give them names. Let's call it U, let's call it V, right? So we are trying to project U on top of V. So according to what we learned before, and please remember that we are doing orthogonal projections. So the projection, the projected vector of U on V is going to be this, right? So perpendicular to the projecting surface, or projection plane, as you can say. So this is going to be our let's call it P, small p, right? So this P vector is going to be the projection of U on V, right? That makes sense. If the lights were shining from exactly the top, this would be our shadow, right? The shadow of this vector on top of this vector. Alright, so let's get rid of the lights. Okay, so what is the value of P, or how can we calculate P? Determine the mathematical formulas of P. Alright, so the formulation begins from one simple fact, that is this part here, this vector. Let's try a different color. Okay, red, yeah, why not? So this vector, we call this the error vector. Why? Because we are looking at it this way. So in the line of V, we don't have the vector U, but the closest approximation of U is the vector P. So if we call P as the approximation of U on V, then E is the error vector, right? This the naming error is going to be much clearer to you after the next week when we discuss least square, but just for now let's call it E vector. All right, now we can say U is a summation of the vector P and the vector E, right? So the portion that is on the line of V and the portion that is perpendicular to the line of V, sorry. So E is perpendicular to V. There can be many ways to prove it. The proof is pretty simple. I think you can try that on your own, that E is going to be perpendicular. And it kind of follows from our definition, because in orthogonal projection, we basically projected on top of V and the projection lines were perpendicular to V, right? So it kind of comes intuitively, but of course there is a proof, and the proof is simple, so I'm not gonna go there right now. This is the important part, that U, this vector, is made up of two components, and this component is unique. For U and V, there is only one P and one E. You cannot write it like say the same thing, P1 and E1, like something that is not P and something that is not E1, and they are perpendicular. You cannot write it like this. There is only one way you can write it in this manner: a vector that is parallel to V, a vector that is perpendicular to V. So this is parallel to V, parallel, this is perpendicular to V. All right, so the property we are going to focus on is that the vector E is perpendicular to V, right? And one more thing, P is parallel to V, which means P is basically a scaled version of V. So we can write P is equal to, let's say, xV, right? Where x is a scalar. So if I scale V by some factor, I'll get to P, because they are on the same line. So we are going to use these two things. One thing is E vector is perpendicular to V, and the fact that P vector is parallel to V. Now, if two vectors are perpendicular to each other, what do we know? That their dot product is 0. So what are the two perpendicular vectors here? We have got P and E. They are perpendicular to each other. What is P? P is xv. xv. All right. Wait a minute. Sorry. Okay. So V is perpendicular to E. So we know V. Let's go line by line. I think it's a. Why can I write? Okay. So sorry about all that messy stuff. Okay. So we know V is perpendicular to E. So V dot E is equal to 0. Now, what is E? E is basically U minus P, right? So V dot U minus P is equal to 0. So this is the dot product. So we can write V T U minus P is equal to 0 from the definition of dot products in this vector space. And then U minus P. What is P? From this we know P is xv, right? So I'm going from here to here. So V transpose U minus, I'm not writing the vector signs anymore, just for my convenience. P is equal to V xv, right? X is scalar. Achha, let's write the vector signs. Equal to 0. So VTU minus VT xv. X is a scalar, so I'm going to bring that outside, is equal to 0, which gives me VTU equal to X VTV. From here I get my formula. What is X? X is equal to VTU divided by VTV. What is X? X is the scaling factor of V that gives me the projection matrix. So if I multiply X with V, I get the projected matrix. So if I multiply X with the vector V, I get the projection matrix. So this is P. So this is my formula. So if I am, so okay, sorry. So let's write it in general. I'm trying to project the vector B on top of the vector A. So the projection of B on A, this is how you write it, is, what was it? VTU. So we are trying to project B here. So this is going to be A transpose B and A transpose A into the vector A, right? So this is the formula of projecting one vector on another. Alright, so let's see an example. What we're trying to do here, we are trying to project this vector u on top of this vector v. So we are trying to find projection of u on v, right? And we know the formula for that is v transpose u divided by v transpose v into the vector v itself. All right, so let's see, what is v transpose u? V is 4 2 and u is, okay, sorry, okay, 4 2 and u is 1 3. So if we what do you get? V transpose u, we get 4 plus 2 into 3 6, so we get 10 on top. We have v transpose v, which is just the square of v's magnitude, which is 4 into 4, which is 16, plus 2 into 2, which is 20. We get 20 at the bottom. We have got v, the vector v. The vector v is Okay, let's keep it like that. So half of vector v is 4, 2. Half of that is going to be, half of vector v is going to be the vector 2, 1, right? 2, 1. Let's see if our answer is right. 2, 1, this is the point, and if we try to project this, yeah, that does look right. So this does look like the projection of u on v, right? So this is how you do it for two vectors. You're projecting one vector on top of another. And in the future, we're going to see how we can project a vector on an entire space.